So welcome to this pre-recording of integration and summation, a lecture in symbolic computation. So we are going to apply the fundamental theorem of calculus to evaluate integrals geometrically to compute areas. So we start out with an expression in one variable. Now, if the antiderivative exists, then we have the following property. The derivative of the antiderivative is the function itself, and if you apply the antiderivative to the derivative, then again you have the function. Very nice. However, in many interesting cases, there is no symbolic antiderivative, and we have to numerically approximate the definite integral. In case there is a symbolic antiderivative, then we can apply the fundamental theorem of calculus to evaluate the integral by the evaluation of the antiderivative at the bounds of the integration integral. Now, stated here, this is not really a complete version of this theorem. There are limitations on the use of this theorem. So, as I will try to illustrate with the next example. So, if we compute symbolically, we compute exact without any error, but often the results can still be really wrong. So the fundamental theorem of calculus, as stated here, is subject to conditions, and I will hint at these conditions at the next example. Suppose that we apply this fundamental theorem of calculus to the function 1 over x to the power 2, then this function has a symbolic antiderivative. You can see this by taking the derivative of minus 1 over x, which is also written as minus x times x to the power minus 1. Now, the application then of the fundamental theorem of calculus evaluates this antiderivative at x equals b and x equals a. So this is the formal notation written here. So f of b minus f of a. One can simplify this a little bit. However, the main point of this slide is that this result is completely wrong if the interval AB contains the origin. So the symbolic antiderivative and also the original integrand is not defined at x equals 0. So geometrically you can see that there is a vertical asymptote there, and the area of this integral then, so the area that is defined by this integral is actually not really what this expression is, minus 1 over b minus 1 over a. So one needs to be careful. So the fundamental theorem of calculus applies only if the integration interval is free of singularities. So the full statement is that the integrand and also the antiderivative must be nice everywhere over this integration interval a, b. Okay, so integrals are actually limit cases of sums. So we can apply symbolic computation to give explicit formulas for sums. So this is extremely useful. So here we have a summation of n terms, which would require n minus 1 additions to compute, but there is a very simple explicit formula that gives the exact value of this sum. Another case is the geometric sum. So we are summing powers of some ratio. If the ratio is 1, then you actually have n plus 1. So assume now that the ratio is a little bit more interesting than 1. So also here now you are essentially evaluating a polynomial with constant terms. And this polynomial can actually be evaluated a lot easier than the evaluation of a polynomial. So we have this nice explicit formula, and here you see why this formula in principle only holds for r, the ratio different from 1. But we can take limits. So in the limits, so now we don't let n go to infinity, we let go the ratio go to 1, then we will see that this ratio equals n plus 1, which is the actual value of the sum in that case. Okay, one last limit. So we can look at sums where the upper bound goes to infinity. In a way, this is also one definition of the integrals as limits. Then in this example here, this limit equals pi square over 6. We will illustrate that Sage has capabilities for evaluating this limit. Okay, so that is the main introduction to the ideas that I will illustrate next in a SageMath notebook, the Jupyter notebook with the SageMath kernel. So let me swap the Jupyter notebook for the slides. So I have prepared a Jupyter notebook, but let me make a new Jupyter notebook from scratch, which adds to the dynamic nature of the lecture. So this is already our lecture 23, where we consider integration and summation. So we start by symbolic, by making the distinction between symbolic and numeric integration. So this is my notebook that I will use for the recording. So let us consider a very simple expression. So I have the cosine of x, and I will define this as an expression, and this should be executed in a code cell. So I can ask for the derivative of this expression, and I can ask for the antiderivative, either the integral or I can use the integrate. To illustrate that these operations commute, I can take the integrate, the integral of the derivative, so this is a nested operation, or I can take the derivative of the antiderivative. So in both cases I obtain the cosine. I was thinking about the sign, so I wrote the S. So here everything works out very nice. So symbolic integration is the antiderivative operator, and it commutes with the derivative operator. However, in many interesting cases, there is no symbolic antiderivative. So here is an example. Perhaps I should use a g function. So we have the cosine of an exponential. Let me take the composition of three functions: the square, the exponential, and the cosine. If I now ask for the integral of g with respect to x, then it takes a while, and we get the expression essentially back. Okay, so let me now make an expression of the definite integral. So I will ask for the integral of g of x, where x ranges between 0 and 1, and I will ask Sage to hold off on the integration. So sometimes it will take a while for SageMath to figure out that there is no symbolic antiderivative. So you can save yourself the wait by holding off on the evaluation. So this is, by the way, also very useful if you want a symbolic representation of the integral. Also, I point out the syntax for the definite integral. We give a tuple starting with the symbol for the variable in the expression, and then followed by the lower and the upper bounds of the integral. And now we can ask for a numerical approximation, which is very similar how we computed numerical approximations of pi, of any mathematical constant. So here you see a 16 decimal approximation of this definite integral. Now, unlike, there is actually not really a very quick check on the accuracy, so we have to believe Sage that this worked fine. So integrals are actually therefore a lot harder to compute because of the verification process, which is not so immediate. Okay, let me consider now symbolic bounds. So what are the problems when we do the symbolic evaluation of an integral? So if a symbolic antiderivative exists, so if the symbolic antiderivative f, capital F, of little f exists, then we have that the integral, the definite integral of the function f of x, can be obtained by simply evaluating the antiderivative at the bounds. So this is the fundamental theorem of calculus. A very important result. However, how stated here, it's actually not complete the function for the statement to hold, both the function f and f must be free of singularities for all x inside the interval a and b. So in order to make the point here, I will construct a function that has singularities. So consider 1 over x squared. Then we can compute the antiderivative by integrating. So that's my capital F. And actually, why do I take a negative? So I should have taken a positive. And now the integral, so the symbolic value of the integral is then capital F x equals b minus capital F at x equals a. And a and b are not defined, so I should have declared the variables a and b. And here we get the symbolic expression, which is wrong. So let me make that point. The computed value, symbolic value of the integral is wrong. And Sage actually knows this, so let me do the integral of f for x, a, and b. And here you see that Sage is quite angry at us for asking this, so it gives us rather aggressively a runtime error. But looking through the messages, we may get a hint of where it went wrong. So it's also kind of good that the error comes from maxima, one of the components in Sage. And here you see that the integral is divergent. It's for us kind of nice to see what is happening. For if this is your first time using SageMath, then this might be rather scary, seeing these kind of very extensive. But there is a missing assumption here. So C assume. So I will indicate now how you can how you can ask Sage for a good result. So, and that's by using the assume. So here the summary is interesting. So it actually suggests that we should assume that b minus a is positive. So if we can answer the question, is b minus a negative or 0, then we can solve this integral. So let me copy that as the conclusion of this error. So if we can answer the question, so let me see if I can paste this correctly, then SageMath or maxima in particular will be able to provide a good answer. So before we do get into the assume, let's make the plot. So I will make the plot of f for x in -1, 1. And to have a nice plot, I will let y max the maximal value for y being 100. Otherwise, you would just see a very not really such a good plot, because the value goes all the way to infinity. Okay, so there is a singularity. So in particular, the function does not exist at the origin, so we can't really evaluate the function there. Also not the antiderivative. So therefore, let me assume, we can assume that b minus a is positive. So that means that that's actually the question that we were answering. That was the suggestion. So now I can evaluate the integral, and I still have the runtime error. Let me make it more explicit. I can avoid that a and b, so I have this assumption. Let me assume that they are both positive. And now I have made too many assumptions. So I will clear the assumptions by redeclaring a and b, and I will assume that a is positive, and I will assume that also b, that they are both positive values. Okay, the assumption remains still redundant. And how is that possible? So it suffices apparently that it might still be that one of the assumptions is still there. I cannot reset entirely because then I will lose f, but perhaps let me redo this. Or no. So I have that now the value of the integral is valid. So we see that after adding the assumption on a, that we obtain a valid symbolic result. Okay, so the integration is a limiting case of summation, so that will be my third section in this Jupyter notebook. So SageMath contains, we can ask for the symbolic value of the sum for the first k positive integers. Okay, so I can define this by the sum in SageMath. So we have the sum from Python, but SageMath also defines another sum, which I will demonstrate now. So I'm going to use that sum to write down the sum. So I need symbols k and n. So the sum that I will define is the sum of k for k going from 1 to n, and I will keep this as the symbolic sum. So hold off a little bit. So the hold is also hold setting hold to true is also a very good check on the correctness, syntactical correctness of the expression that has been typed in. I can now evaluate the sum by the unhold. So the value of the sum I will denote this by the little s, and make a statement. So the show of the capital S equals the little s. It should be the unhold, not the hold. Here we go. We can still make it a little bit prettier by factoring. So we have the common factor n that's in there, and I can factor this. And perhaps let me complete the exercise by using the show, or more specifically I can do show of s equals the factored form. Okay, so that's one of our summations. So the other summation that we looked at was the geometric sum. So the geometric sum is for some ratio r is defined by the following expression. So now I let the index k go from 0, so we start with 1, r to the power 0, so I go from 0 to n. So I can also express this with a formal sum after declaring the variable. So I have the formal sum, so this will be the SageMath sum of r to the power k, where k was already defined as a symbol, also s is the symbol. And here let me again do hold equals true. And show gives me then this expression, so the nicely formatted formula. I can ask now for the actual sum with the unhold. And what comes out is the symbolic expression for the geometric sum. Notice that this expression, evaluating this expression for, so evaluating s for r equals 1 cannot happen directly, but must be done via a limit. So there is the limit method that we can apply to an expression. So in a way this is a more general way to evaluate an expression where you have potential problems. The problem that we have is that when we plug in r in the expression is that we see 0 divided by 0, r equals 1. So if we plug in the limit, then we have n. So the sum of the first n numbers equals n. The problem is that I see now that I made a typo. The index should have started from 0. So let me redo it. So here the LaTeX typesetting started the index from 0, but then as I was focusing on the hold, I forgot about the index here, and I only noticed it when I was considering the expression. So now we have n plus 1. So let me look at, to end, let me look at another limit. So we can consider limits of sums where the upper bound goes to infinity. So the infinity in SageMath is denoted by the double O. So what is the limit that I want to use? So we can, as example, consider the following. So I can look at the sum. Now again for k equals to 1 to infinity of 1 over k squared. And that limit will be, just leave it a little bit open. So we can actually directly type this in Sage. I can ask for the limit of 1 over k. Perhaps let me be a little bit more careful. So again, type in the sum, and k goes from 1 to infinity. Hold equals true. Now, what will the unhold give us? So let's see. And you see that the answer comes up rather immediately. So alternatively, one can define the sum for an n and then ask for the limit. So that might be the last thing that I want to show. So I can define the sum as the sum of 1 over k square, where now k goes from 1 to n. And most likely I can do immediately limit n equals infinity, and I must do the unhold apparently, or that is not a good thing to do. So let me do the unhold. That will evaluate the expression. And here you see I get the harmonic numbers. So the harmonic numbers are defined as the reciprocals of the first n natural positive integers. So you can't take 1 over 0. And we have these 2 here because we take the square. So let's see if I can take the limit operation for n equals infinity, if that is going to work. Yes and no, it somehow does not evaluate this to the fullest. Okay, I will stop here. The main point of this lecture is that one has to be careful with the symbolic bounds. We illustrated many good applications of the hold. One can do this for pure typesetting reasons, that you want to see the result nicely typesetted. So this is a way of preventing the evaluation. It's also in the context of numerical integration. It's a very good way of saving time. So if there is no symbolic antiderivative, like in this example here, then one simply tells Sage, don't bother to try to evaluate this antiderivative, to compute this integral symbolically. And then you do the numerical approximation directly, like we did with the approximations of the transcendental constants such as pi. Okay, I hope that this was an interesting lecture. So this lecture is shorter than the previous one, so in some sense a little bit compensation for the amount of material here.